Hello, my name is Andrei Poenaru. I'm part of the HPC research group at the University of Bristol in the UK. And today I'm going to present to you some performance results from the Fujitsu A64FX on real HPC applications. This work that I'm going to go through has been done partly by members of our group and partly by some of our colleagues at Sandia. Most of this work is done on Izambard. Izambard is a tier 2 HPC facility in the UK. It's a regional supercomputing center run by a few partners, which started in 2016-17 and was the first 64-bit ARM production supercomputer. It has been a great success. It has been running in production since. And last year it was updated to double the compute capacity of the ARM phase and also to expand it with some additional architectures and new computation facilities. The main part of Izambard is the ThunderX2 system, which has about 330 nodes of 32-core ThunderX2. This is a Cray XC50 Scout system with Aries interconnect. And joined together with that is what we call the Max, the multi-architecture comparison system. This is a small cluster with different kinds of nodes of the latest architectures available from the various vendors. We have some Intel, some AMD CPUs and GPUs, and some NVIDIA GPUs as well. And the new in Izambard 2 is the HP Apollo 80 system, which houses about 72 nodes of the A64FX from Fujitsu. All of this is hosted in Exeter by the Met Office. The interesting part for this year is the HP Apollo system. There are about 72 nodes making almost 3,500 cores. Each has about a terabyte second of memory bandwidth. It's connected together using 100 gigabit second InfiniBand, and it supports the full software stack from Cray with all the different compilers, including Cray's own compiler, the open source GCC compiler, the ARM compiler, and Fujitsu's own compiler for the A64FX. The chips are the same ones that are in Fugaku in Japan. The only difference is a slight difference in frequency. Ours run at 1.8 gigahertz, theirs run at 2.2. The Fujitsu A64FX chips are 48 core. They have HBM2 memory. Each core has 512-bit SVE vectors. And the chip is split into 4 groups, which are called core memory groups, or CMGs. This is important because each of these groups, as you can see in this diagram, forms a separate NUMA node. Each of these groups is connected directly to a stack of HBM memory. It uses about 170 watts, and in our system, it is connected to InfiniBand network. A few years ago, when we installed the ThunderX2 system, it was very interesting to compare these new ARM processors against other mainstream HPC hardware. It was the first time when ARM was making its way into HPC, and there are a lot of interesting performance comparisons we can make there. But now, since then, a number of different new ARM processors have made their way into the HPC market, and we're now at a point where we can make similar comparisons using just ARM platforms. And this is what I'm going to be showing to you today. I've taken the latest 4 ARM-based CPUs that are used in HPC, and I'm going to show you some performance results from a wide range of benchmarks run on those. The platforms that I'm going to be using are the Fujitsu A64FX, the Graviton 2, which is a processor from Amazon that you can use in the AWS compute cloud, the Ampere Ultra, and the Marvell ThunderX2 as we have in the Izambard system. Now, this table has all the technical specifications of these processors. One thing that's important to note is that the Fujitsu A64FX and the AWS Graviton 2 are single socket processors. The other 2 are dual socket. You can see here the clock speeds and the peak compute performance and memory bandwidth performance. On all of these platforms, we haven't done anything special. We didn't need to set them up in any way, in particular to prepare them, so to say, for HPC. We use the standard platforms. We install the compilers that can target these platforms. We're using the latest version of all the available compilers. So ARM and GNU, for example, they can target all of these processors. On our Izambard Cray system, we can use the Cray compiler to target A64FX and ThunderX2. And then Fujitsu has their own dedicated compiler which targets A64FX. And one note that's important to make here is that the Fujitsu compiler can be used in 2 separate modes. It has 2 separate front ends, and the performance that you can get may differ depending on which one you use. There's the traditional one, and there's a newer Clang-based front end. I will point that out in the results when it is relevant. The Cray compiler that we are using on A64FX can generate SVE, but it is a pre-release version, so performance may change in future versions. So what I'm going to do next is go through a few benchmarks. I'm going to show both mini apps and full-scale applications. I'm going to look at both memory bandwidth bound problems and compute bound problems to get a better understanding of how these platforms compare one to each other. The first is BBLStream. BBLStream is a implementation of the stream benchmark in C++ and many different programming models. For this, I'm just using the standard OpenMP implementation, and I'm looking at the performance of the triad kernel. This graph shows the achieved bandwidth in gigabytes a second, so a higher number is a better result. And you can see each cluster corresponds to one of the processors I had on the previous slide, and then each color shows a different compiler used on that platform. Again, the compiler versions are the latest that can be used on these platforms. What we can see here is that the A64FX does achieve a high fraction of the 1 terabyte a second peak memory bandwidth. There is a difference here between the performance obtained with the Fujitsu compiler and the performance obtained with the other compilers, because Fujitsu uses a zero fill instruction to essentially avoid reading data from cache before writing back into it. So this improves the memory bandwidth slightly. There are some further tweaking and tuning you can do with flags, and you can increase this number a little bit. But what's also important with the Fujitsu compiler is you can set some environment variables to instruct it how to allocate pages. And because, remember, the A64FX has those 4 CMGs, which are separate NUMA nodes, it is important to tell it to allocate memory pages on the NUMA nodes where they are going to be used. Depending on what your system is, this may not be the default. And if this doesn't happen, then a lot of the memory will get allocated in the first NUMA node, and essentially you won't be utilizing all 4 to a similar amount. Next, I've got Cloverleaf. It is a hydrodynamics mini app. It's generally memory bandwidth bound, but there's also some arithmetic in it. There are some divisions and there's some trigonometry functions. And these are interesting to look at on the A64FX because of the out of order architecture of the A64FX, which is different from most other processors we're used to in the HPC environment. It is really important that the compiler can treat these properly to obtain good performance. This is a graph that shows time. So a lower bar is better now. Everything else is the same as before. We can see that with the Fujitsu compiler, the benefit of the HBM2 memory is clear. This is the fastest result that we achieve here. The ARM compiler also does well. There is a particular flag that you can use to tell it to rewrite divisions using an iterative reciprocal algorithm. This sacrifices a little bit of precision, but if you can tolerate that, then it really helps with performance on the A64FX. And then the performance that we saw from GCC was much lower because the SV code it produced was not great quality. Now, Cloverleaf is a hybrid MPI plus OpenMP application. And here I'm showing you the best results from all these configurations. So I've run many different configurations, and these are the best. But it's interesting to look into what is the best configuration and how it compares to the other ones. So in this graph, this is just on the A64FX. This is the only platform here. The clusters now represent a compiler each. In each of the bars is a separate way to run the application. The first one is flat MPI, so that fills all the cores with MPI ranks. The next one is flat OpenMP, which uses threads and just a single MPI rank. And the third one is hybrid MPI plus OpenMP. Here, I'm using one MPI rank per CMG, and then I'm filling all the cores of that CMG with OpenMP threads. In general, what we've noticed is that the best result is achieved with hybrid MPI plus OpenMP. This graph shows relative performance normalized in each cluster. So the bar that scores 1 is the highest performing option for that compiler. And we can see in 3 of the 4 cases, that's the hybrid OpenMP one. The OpenMP performance was different, and depending on which compiler you use, you may see better or worse performance. These results are slightly different from what we're used to seeing on the other platforms. Flat MPI is usually a good choice on most other platforms we've seen. Hybrid is also good, but it's not usually the case that it's faster or at least significantly faster than flat MPI. Flat OpenMP is, of course, slower when you're dealing with a multi-socket system. Now, a similar experiment was done by our colleagues at Sandia, who use the Sparta mini app. This is a direct simulation Monte Carlo application. It scales really well. It uses MPI, and it can use threads using Cocos. Using Cocos, you can use the OpenMP backend to use threads through OpenMP, essentially. And what they found was different than what we found with Cloverleaf. In their results, it is because this is a time graph, it is the flat MPI result that was fastest. This seems to happen even when you're using optimized versions of Cocos that support the A64FX, so you can use the latest version of Cocos, and the performance that you get from adding threads is still not quite the same as adding as not adding threads and using flat MPI. The next benchmark I have is OpenFoam. We're using the version 2006 of OpenFoam and the driver test case. This is the same test case that we've used on Izambard before and compared it with other systems. It has about 11 million cells. And this graph shows the benchmark time with the time taken for the first step discarded. This is to remove any variation from I/O and preparation and so on. I was not able to obtain a result with the Cray compiler here because of compilation errors. But in general, the performance of this benchmark relates very well to memory bandwidth. There is some compute that matters, but vectorization is very low for this application. So in this case, we're seeing some performance improvement from the A64FX due to the HBM2, but we're actually seeing very good performance from the Ampere Ultra, which, even though it doesn't have HBM2, it does have high bandwidth DDR4 memory, and it has a lot of cores. Because vectorization is low, then even though the Ultra has 128-bit vectors, by having more cores, it essentially is able to outperform the A64FX. In fact, the Ultra result that we got is very close to what we get on Rome, which is currently the fastest result that we have for this benchmark. One of the things that the Ampere Ultra and the Rome both have in common is that they have large caches, so this may play a role in this benchmark. Next, I have Minibute. We're now moving more into the realm of compute-bound applications. Minibute is a mini app that we've developed at the university. It is based on a molecular docking application, which was previously developed at Bristol as well. It is very optimized. It achieves a very high fraction of the peak compute performance for a number of different platforms. And on the A64FX, it's a great example of how you can benefit from using a compiler that optimizes well for the platform. If your compiler is able to do unrolling, software pipelining, and interleaving of the loop, it's able to achieve really good performance. If the compilers can't tune as well for the A64FX, then performance is slower, perhaps even lower than a ThunderX2. Again, we're seeing the Ampere Ultra with really good performance here. This is because of the high number of cores. Bude and Minibute parallelize very well, so we're easily able to distribute work to all the 160 cores on the Ampere Ultra. Again, the Ultra here is competitive with the latest Cascade Lake and Rome processors. The main limitation for the other processors is the vector length. Because they use 128-bit vectors, they struggle to get closer to something like Cascade Lake, which uses 512 bits again. If you're interested in hearing more about Minibute, there's a reference at the end. We have published a paper here at ISC and the main track in the performance portability track. So if you want to see more results, including on the A64FX, I invite you to have a look at the video and the paper for that. Next, I've got MiniFMM, which is a mini app that uses OpenMP tasking. It implements the fast multipole method, and this is an algorithm that's very well suited for task-based parallelism. What we can see here is that the differences between the compilers are very small, partly because there isn't that much vectorization happening, and also because the difference between running lots of threads and not that many threads is smaller than it was the case with Minibute previously. For example, if you go over above 60 threads, you don't really see the performance increasing anymore. And on Ultra, if you use all the cores, you actually get slower performance. So I had to reduce the number of threads I ran to get this optimal result here. We're seeing a slow result from the Cray compiler because the SVE early access version that we have used here is based on the older proprietary Cray frontend, as opposed to the newer Clang-based one. And that seems to have some trouble with OpenMP tasking. And the last benchmark I'm going to show is Gromacs. Gromacs is widely used in computational chemistry and molecular dynamics. We're using the latest version of benchmark of Gromacs and the integrated PME benchmark. This is a very good test of compute performance. It is perhaps not a very good test of the overall the overall performance of large platforms, because it is limited to 64 threads. So this is a performance graph. They use a metric which is how many pairs you can compute per microsecond, and a higher bar is better. Unfortunately, the A64FX was slower than the other processors we tried here. And the biggest reason for that is Gromacs uses their own hand-tuned SVE intrinsics. This was only usable with the GNU compiler. And you can see that when we used the GNU compiler, performance was much, much better. But with the other ones, we had to fall back to 128-bit neon vectors, which meant we couldn't take advantage of the wide vectors and SVE, essentially. Now, Gromacs can use different FFT libraries, and in some benchmarks, it does matter. Not so much for this one. This is almost purely PME, but we did use the matching FFT library. So with the ARM compilers, with the ARM compiler, we used the ARM performance library. With GCC, we used FFTW, and with Fujitsu and Cray, we used their own tuned implementations. If you're interested in Gromacs, I have a reference to a paper at the end where we do some other benchmarks with different compute characteristics, and I invite you to have a look at that if you want to see some more results. So that was the last benchmark I wanted to show. Now to talk a bit about what it's been like working with these processors. And a few years ago, when we just installed the ThunderX2 system, our conclusion was that everything worked out of the box and it was really easy to work with. And from that perspective, nothing's changed. It's essentially the same here. All of these platforms, processors are supported by compilers. It's important that you use a new compiler that targets your processor. In these results, for example, I've used the GCC versions that were just released in May. And where we've seen some shortcomings, these libraries are also are always being improved, and we expect performance to keep going up as time goes on, which is why we plan to look at more benchmarks in the future to see how this evolves and how it changes over time. In general, the A64FX has been easy to work with, just like other CPUs. You need to be aware of the 4 CMGs configuration, which the CMGs which are treated as different NUMA nodes. It is particularly important to pay attention to core binding and placement. So perhaps use something like XT high to make sure you're placing your ranks where you want them to be. And because the out of order architecture is a bit different, it really benefits from a compiler that can optimize well for it. The A64FX also has a configurable sector cache, and some other groups have done some really great work showing how you can use that if you really want to tune the performance of your application. If you're interested in these things, if these sound good to you and you would want to get involved in similar experiments, please apply for an account on Izambard. We have time dedicated exactly for this sort of performance, portability, and comparison experiments. And with the lots of different architectures available in one system, Izambard is the is a great place to get started with experiments like this. Yes. So in summary, the A64FX shows great performance potential. Depending on your workload, it can beat the cutting edge competition from Intel and AMD. Performance is really good. It is really easy to use. And as long as you're using the right tools and libraries, you will obtain good performance from it overall. This is all I had to say. Here are some links to our group's homepage. There's also some links to some GitHub repositories. If you want to have a look at more detail about how these benchmarks were run, and maybe you want to reproduce the results yourselves, you can find the scripts here and benchmark output as well. And if you're using Izambard or want to get started with it, here are some docs. And finally, here are the papers that I mentioned in this presentation. This is the paper on Minibute that we published here at ISC. Please go and have a look at that video and the paper. It's in the main track. And if you want to see some more results from the A64FX, we have published these results I've presented and some other ones in a paper submitted to CUG, which should be published soon, and you will be able to read that as well. With that, thank you for watching, and see you soon.